Right. Thank you. And thanks everyone for coming today. My name is Mihkel. I'm an associate professor at University College London and also visiting professor at the University of Tartu in Estonia. And I work on planet formation with the view to figuring out how planets end up with a particular budget of chemical elements that they have. And so hence the title of the talk, The Origins of Planetary Chemical Diversity. And what I'll try to do in this talk is to have some sort of balance of big picture, talk a little bit about planet formation and in particular the so-called CHNOPS elements or CHNOPS elements that are considered most important for Earth-like biospheres in the long run. But then also have a few case studies of what exactly we're doing to improve our understanding of these elements in planet-forming environments, and then how that might help us to have better models in terms of predictive ability to predict the chemical composition of planetary solid cores and planetary atmospheres. And before I proceed, I actually would like to just highlight that really without PhD students, very little work would get done in the field of astrophysics. And so I really want to highlight the PhD students that either I have worked with or I'm working with at University College London. Luke Kite, who's now a postdoc at Queen Mary University, Can, Anna, and Jason, who are currently working at UCL, and then students from the University of Tartu, Sandipan, who's actually doing a double PhD, also based in Graz in Austria, and Veronika and Alexandra working in Tartu. And broadly speaking, these two groups are spread between planet formation and planet-forming disks in UCL, and then the properties of disk and planet hosting stars at the University of Tartu. That's the broad distinction. And so we cover a lot of areas from observation, spectroscopy of protoplanetary disks where planets form, modeling of those same disks, both from physics and chemistry, and then tying that to the properties of stars and planetary systems. The outline of the talk. So just to quickly recap, we'll talk about the diversity of planets and disks, why these particular elements, the CHNOPS elements, a little introduction to planet formation, linking planet composition to formation. So we'll look specifically at some models attempting to predict the chemical composition of planets and use that to motivate our case studies for carbon, oxygen, sulfur, and phosphorus, and then summarize some of the points and findings. So this figure crops up often in exoplanet talks, and this particular one is a few years old, but the broad shape has not really changed. So what you see here on the x-axis is the orbital period of planets around their host stars. So planets, as most of you will probably know, right, are objects that are not massive enough to undergo internal nuclear fusion processes, but are big enough to be spherical under their own self-gravity. So they're bigger than big rocks or big mountains, and they're smaller than the smallest stars. Okay, so the orbital period on the x-axis and then mass on the y-axis. So the mass range goes from, in Jupiter masses, from a thousandth of a Jupiter mass to somewhere around 20 Jupiter masses, which is about the boundary where you get so something that's called brown dwarfs. So not quite planets anymore. And you see this diagonal envelope cutting across the middle of the diagram. That's sort of the sensitivity bias of where planets are more easily able to be found. So high mass planets can be found at larger orbital distances from their central star more easily, while low mass planets can really mainly be found so far very close to their stars. Just for reference, the Earth would be here around 365 days, of course, 1 year. And in terms of Jupiter masses, I think the range you want to think about is about 1% of a Jupiter mass. So you can see that the region where Earth would be is pretty much empty at the moment. Okay, so, but there is a huge diversity in orders of magnitude of planet masses and orbital locations, and I just want to underline that if you didn't have that clear in your head already. And this is only in terms of period and mass. So the next question that the field is asking, or one of the next questions that the field is asking, is what is the extent of chemical diversity between all of these planets? So are they all similar to each other? How different are they? And how does that come about? And that's what we're trying to understand. We now know that planets form in protoplanetary disks around young stars. So these are live for about 10 million years. It's a disk of gas and microscopic to macroscopic solid particles. We see in the latest high-resolution studies of dust thermal emission from these environments that the disks are not smooth, but actually the solid particles are distributed in mainly in rings or sometimes in spirals. Also, the disk sizes are very different, so these are all to scale with each other. You see a gallery. These are not actually next to each other, just to be clear. It's sort of thumbnails of different disks around young stars. And the size scales we're looking at here are somewhere, the largest disks we see are a few times larger than the orbit of Neptune in the solar system. So let's say sort of broadly, we're looking at a few times larger spatial scales than the entire solar system in terms of its planets. So we go to hundreds of astronomical units. And in a few cases, the disks are much smaller than that. In a few cases, larger than that. So there's a lot of diversity and also a lot of diversity in how the solid particles are distributed. And we'll come to why that matters. Similarly, for the gas, this is actually just out today, a press release from the EXO-ALMA project led by Richard Teague. And you see here spectacular images of carbon monoxide gas, which is one of the key probes of gas in planet-forming disks. You can sort of see the toroidal structure of the gas, and you can start to make out some idea that there are maybe ring-like structures in a few cases. In other cases, the disks are sort of remarkably symmetric and uniform, and so on. So, what exactly is happening inside of these disks, and how does that lead to specific outcomes in terms of planets? That's our question, to unravel the formation history of planets in these protoplanetary disks. So say we observe a particular planet, that's planet A in this figure, and we want to know what is the formation history of that planet? What are the possible different trajectories that the planet took as it was growing in one of these protoplanetary disks? Did it end up in a different location from where it started, and what kind of composition did it inherit, and so on? Our particular angle focuses on the chemical composition. So for that purpose, I'm highlighting a subset of elements from the periodic table. This is the so-called astronomer's periodic table, and it highlights the most abundant chemical elements in the universe. So hydrogen being the most abundant, and helium. But really what we're going to be mostly interested in here is carbon, nitrogen, oxygen, sulfur, and actually phosphorus, which is not listed here because it's not quite abundant enough. So these are the sort of volatile and semi-volatile elements, so to speak. We'll come to what that means in 2 or 3 slides from now. The other important elements that are highlighted here, iron, calcium, aluminium, these are so-called rock-forming elements that are easily locked up in solid particles, and they are important, but in a sense less interesting because you probably don't get quite as much diversity in their chemical behavior in planet-forming environments. So in a sense, you could say probably most of the time planets will inherit a similar ratio of, say, iron and calcium. But that is not so obvious for something like the ratio of carbon to oxygen or carbon to calcium, and that's the interesting part. Now, if we compare that with the elemental mass budget of the Earth's biosphere, represented here by a human, okay, it's a little bit anthropocentric, but broadly speaking, all living creatures on the Earth have similar content of chemical elements. So you can see, of course, hydrogen is not massively important in humans, being a very volatile gas. It's present, but it's not dominant. Oxygen is very abundant. Carbon is very abundant. Hydrogen, mainly because it also participates in water, right? H2O and carbon-bearing compounds. Then we have nitrogen, calcium, and phosphorus, which is considered a really bioessential element, something that in at least terrestrial biosphere so far seems to be very, very difficult to replace in terms of its functionality in an Earth-like biochemistry. So phosphorus is of growing interest to people in the astrobiology community, trying to understand the origins of life and Earth-like biospheres. And we also see potassium, sulfur, sodium, chlorine, magnesium, and then other elements. So let's just say the proportions end up vastly different from what they are in terms of availability in the universe. Though a lot of the key players are similar, their abundance ratios have changed quite a lot by the time you get to biochemistry. So that's a long journey from the interstellar medium and different atoms all the way to planets and life. One of the details we need to understand before we get to planet formation theory is the so-called volatile, semi-volatile, or semi-refractory and refractory chemical elements. And that's shown here. On the x-axis, we have the condensation temperature of a chemical element. That essentially shows us that if we started with a very hot, extremely hot, let's say, atomic gas, and started to cool that down, and at each temperature we let it fully equilibrate in a chemical sense, then what's the temperature at which 50% of a given chemical element was already condensed into solid particles? So you can imagine if you have a very hot gas, you start cooling it, eventually solids start to form. Things stop being a gas, just like water vapor would condense in cold conditions. So you can see titanium, iron, aluminium, calcium, the sort of really robust rock-forming chemical elements. Then you have the semi-refractories or semi-volatiles, such as sulfur, and phosphorus is sort of getting close to that as well. These are elements which have lower condensation temperatures. And in a sense, that means that chemical kinetics has more of a chance to be at play potentially for these elements, also in star and planet forming environments. And then we have the really volatile elements like carbon, nitrogen, oxygen, which don't really start to condense in earnest until you get to below 1 or 200 Kelvin. So that's very low temperatures in an absolute sense. That makes their chemistry very interesting, but also very difficult to fully predict from first principles because the initial conditions matter, the chemical kinetics matter, and you cannot use equilibrium assumptions to model what those elements are doing. Unlike something like titanium, where the outcome is usually quite clear in terms of it being in specific types of oxide mineral rocks. So this is just to give you the context of the dynamic range of condensation temperature and behavior of elements. And you can hopefully see that if we, what's shown on the y-axis actually is the abundance of these elements in the gas phase in the interstellar medium. So that's really very diffuse gas before stars and planets start to form from it. And you can see that already there between the stars, the refractory elements, the dust-forming elements, are missing from the gas, right? They have a lower abundance. So those dust particles already exist in interstellar space. But for the semi-volatile or semi-refractory elements, that does not seem to be the case. And so in a way, that's very interesting already because it tells us that these elements that are easily or relatively easily locked in solids are still present almost entirely in the gas in the interstellar medium. And that's what one of the points sort of illustrating why I said we need to know the initial conditions and we need to have empirical data on what these elements are doing because that really matters. We can't rely on just an easy parameter like condensation temperature to fully predict where these elements end up. I should add that the dust in the interstellar medium is much colder than say 400 or 500 Kelvin. So these elements are not thermally sublimated into the gas, right? So just to underline that this is perhaps at first sight somewhat surprising that they are in atomic gas, and we really need data to show us that. All right, and I've also used the Arecibo message, which was sent in the 1970s from the now decommissioned Arecibo radio telescope towards a globular cluster in our own galaxy. And the attempt was in a, I'd say, somewhat playful but still interesting way to encode information about life on Earth and our civilization. And one of the key bits of information that was coded into there is the carbon, hydrogen, nitrogen, oxygen, and phosphorus elements that you see in purple at the top of that message. And the reason for that was because they are so important for our biochemistry. So that's why the proton number of these elements was encoded into the Arecibo message that was sent to our galaxy in the hope that perhaps some alien civilization in the future might pick it up. But in a way, it shows that this matters to us, right? This is what we consider essential for life on Earth, these elements. All right, and now jumping already ahead to elements like phosphorus. Well, you may remember that from a few years ago, there was a big debate around whether there's phosphine gas in a relatively high amount in the atmosphere of Venus and how surprising that was. And if true, this discovery could potentially be a sign of some sort of biochemistry happening, perhaps microbial type activity in the atmosphere of Venus. Now, the debate is still ongoing on what exactly is actually going on with the possible phosphine detection in Venus's atmosphere. So surely there will be more news on that. But just to underline that this is actually a very hot debate, and the one of the important aspects here is in order to reliably interpret potential biosignatures in other planets' atmospheres, we do need to understand something about what is the starting budget of the elements relevant for those biosignatures. What is the starting budget of those elements in the planets, right? How much is locked in a planet's core? How much is locked initially in its atmosphere, and how does that then evolve over perhaps billions of years? So this just further underlines why we want to understand what each of these chemical elements is doing in planet-forming environments. Now, the knowledge of exoplanet atmosphere compositions, while there is some data, in particular on carbon and oxygen, already available for perhaps a couple of dozen planets. And I know there are people on the call who will have a much better idea of the exact sample size, the latest sample sizes. But let's say carbon and oxygen have been studied already successfully for in the last 15 years or so. But now, with telescopes like the James Webb Space Telescope, which is already flying, and Ariel, which is anticipated to launch in 2029, we will be getting access to some data, at least, on the chemical composition of the atmosphere of first dozens, and then hundreds, and then up to 1,000 exoplanets. So we're moving from the era of characterizing individual planets to really large samples, and that makes it really timely for us to also provide a foundation from the planet formation side that enables to interpret all of this upcoming chemical data on planets. So just a few glimpses of that. So I don't really work on characterizing planets myself, but obviously we have to keep an eye on what our colleagues are doing there, and we collaborate. So here's a detection of sulfur-bearing species, SO2. This is really, in a way, one of the pioneering works, right? Expanding the set of chemical elements that can be measured in exoplanet atmospheres beyond something like carbon, oxygen, and claims of nitrogen detections to also sulfur. So the James Webb Space Telescope facilitated that in the last few years. This is a detection in WASP-39b. And then on the right-hand side is these are just modeled spectra, essentially, of different molecules that in the spectral range accessible to the Ariel Space Telescope, which, as I said, will launch in 2029 if all goes as planned. And you can see that in Ariel's spectral range, you have not only carbon and oxygen-bearing molecules, but also nitrogen, sulfur, and phosphorus, as well as other species. So that's not to say that all of these species will be confirmed in exoplanet atmospheres, but they may be. At least capabilities to detect them in principle are there if they're present in the right abundance ratios. So that's why we want to prepare, right? Um, Now, so before we go to the details of the chemical composition of planet-forming material, just a quick tour of what the modern picture is of planet-forming environments and planet formation processes. Now, what you're seeing here is a cross-section of a protoplanetary disk. So you can imagine the star, which is this orange ball, and then a sort of flat donut type disk around it, and we've taken a cross section from one side of the donut. You can see in light gray, I've highlighted the distribution of gas and very small solid particles that let's call it small dust. Those very small particles are fully coupled to the gas, and so their distribution is very similar to the gas distribution because they're so small. They're like Brownian particles bouncing around between the gas. Then you have the large dust particles. Let's say, let's call them pebbles just for simplicity in this case. Obviously, there's actually a size range of solid particles, not only two different sizes. And these pebble type particles are characterized by being large enough that they're no longer fully collisionally coupled to the gas on a level of individual collisions with gas particles influencing them. They see the gas as a fluid around them. And as a result of that, they start to be hindered by the gas. And that actually leads to the largest dust particles collecting, first collecting on the midplane of the disk and then drifting quite rapidly closer to the central star. So that the details of that don't matter at the moment. It's due to the internal pressure support that the gas has for itself that acts as a sort of anti-gravity that the large dust particles don't feel, essentially. But the interesting bit is that, of course, this means that solid particles, as time goes on, once a star forms with its planet-forming disk, as time goes on, the solid particles increasingly start to behave in a way that's different from the gas. So that adds a lot of complexity to possible outcomes and also makes it quite tricky to predict exactly what will happen. Where will the solids congregate? Because where solids congregate, that's where large particles, macroscopic objects, can start to build up. In the coldest, densest parts of the disk, the dust particles can also be covered by volatile ices. That just means that different kinds of volatile molecules will condense out, freeze out from the gas phase onto the solid particles. The most common species we think of there are water, which carries probably most of the oxygen in the disk, freezes out at something like 100 Kelvin, and carbon monoxide, which carries a lot of the carbon and oxygen, freezes out something like 20 Kelvin. So that's our so-called snow lines. Those are regions where as you get closer to the star, it gets warmer and different kinds of ices can sublimate, evaporate from the solid phase back into the gas. Okay. The disk is evolving, it's being mixed, solids are moving around. There's probably a wind from the surface of the disk removing some of the mass. A lot of the mass accretes onto the central star. There's just a lot of complex kinetics and interplay of processes going on. Now, if you want to get more into the details of all of these different stages of how the solids move and grow, I would recommend a review led by Sebastian Kreit in the Protostars and Planets 7 review conference and book. You can find it on the archive preprint server. So this is a figure that shows the different stages of growth on the y-axis, starting from atoms and molecules, going to small dust particles, going to macroscopic objects, let's say first pebbles and then planetesimals. And then in terms of outcomes, if the bodies stay small enough, they may become terrestrial planets. If they grow beyond a few Earth masses, they may undergo runaway gas accretion and become gas giants. So all of this you can go into the details in not only our review, but the rest of this review book as well. Now, to come back to the sort of simple story that we have for planet formation, I wanted to highlight the two mechanisms, right? So what I've talked about so far is small and large dust particles, and these dust particles can collide, stick, grow, and eventually they can accumulate in local pressure maxima in the protoplanetary disk. So where the gas pressure is not completely uniform, large dust particles will get trapped in those local pressure maxima, and they can collapse to form planetesimals in one go. Those planetesimals will then collide to form planetary embryos, and pebbles and planetesimals will continue to accrete onto this now planetary embryo. As it gradually grows, if it's massive enough, it will accrete gas. There is an alternative pathway, which is if you have a large enough clump of gas and dust that becomes gravitationally bound to itself, and if it can cool fast enough, which can happen in the very outermost regions of a protoplanetary disk, it may be able to just form a gas giant planet in one go through gravitational instability in a protoplanetary disk without requiring any sort of growth process. One of the interesting questions is also, do these two pathways lead to different kinds of planetary compositions? So that's also a partly open question that, of course, a lot of people are investigating. And I just want to highlight that one of the best known relations, or the best known relation so far we have with planetary system outcomes and the initial chemical composition of a planet-forming environment is the so-called planet occurrence metallicity correlation. So this is one representation of many of that relation. It shows on the x-axis the logarithmic so-called metallicity. Let's call it non-hydrogen and helium element content. So basically, broadly speaking, solid content of the star, refractory element content of the star. And on the y-axis, the fraction of systems in the confirmed exoplanet archive where the star has that composition. And so it just shows a small increase here, right? Noticeable increase at metallicities above 0, which means metallicity above that of the sun. And the idea is that having a higher metallicity shows that the birth environment also had a higher abundance of solids relative to the hydrogen gas, and it made it easier for planets to grow. That's the hypothesis, and then you can get giant planets forming more easily, so you end up with a higher occurrence rate. So this is a very bulk view of the chemical composition from planet-forming environments all the way to final planetary systems. There's an interesting nuance also pointed out by Nuno Santos, that actually if you look at the highest planet masses, then that metallicity correlation seems to be weaker. So he was potentially pointing at the highest mass planets forming through a mechanism that does not benefit so much from an increased availability of solids for growth. And while the finger there seems to point at potentially gravitational instability, which where the dependence on metallicity might be more complex. So that's an interesting finding, that perhaps many of the highest mass planets form through gravitational instability, and the so-called normal Jupiter-type planets form through the so-called core accretion gradual growth processes. So this is the best known link between composition in planet-forming disks and the properties of the planetary systems. Now, if we assume that our planets have formed, whether through core accretion or gravitational instability, they will further influence the gas pressure distribution in the disk. And basically, they can lead to large particles increasingly getting trapped in certain radial zones in the disk, the so-called dust traps, dust rings. So large particles of dust will start accumulating there, and then potentially make it even easier for new generations of planetesimals to form, and potentially also maybe leading to a new generation of planet formation in the same disk. So this all takes a few million years, probably typically up to 10 million years maximum. Then, as the planets are embedded in their natal disk, if they are growing to be giant planets, then complex processes will be happening. They may or may not be accreting gas and large solid particles around their equators, right, on the disk midplane. The dust and ice is shown here in white. They may also be accreting gas through so-called meridional flows from the disk atmosphere, so-called the upper layers of the disk, where there are few solid particles. At the same time, the disk is mixing vertically, there's drift going on inwards. All of this to say there's a lot of complexity. And you can see that it really matters if we assume, for example, that 100% of elements like sulfur or phosphorus is locked in rocks, then very quickly, all of our sulfur and phosphorus will end up in large particles on the disk midplane. Whereas if we say 10% or maybe more, in some cases of sulfur or phosphorus is in a more volatile form, more available to gas and ice phase chemistry, then that sulfur, for example, might be available in the disk atmosphere as gas, right? And so the same applies for carbon, for oxygen. We really need to understand the range of diversity you can get in the budget of each of these elements, because that will matter to the range of outcomes we can get in terms of what the composition is of the solids and the gas that planets accrete. Right. Now, once planets have formed, planetesimals may also form in these dust traps, dust belts. Eventually, the gas dissipates. That may take another millions of years, 10 million years. Potentially, you can have residual gas for tens of millions of years in a protoplanetary disk. At the same time, icy planetesimals that are now finally, after the disk dissipates, exposed to the star, can heat up and release second generation gas from all of the carbon monoxide and carbon dioxide, water, all those ices they contain. So we see actually gas-rich debris disks around somewhat older stars. That's a discovery from the last sort of 10 or 15 years as well, that this may be quite common actually. All right, and then eventually you're left with a planetary system with a residual so-called debris disk of planetesimals that occasionally collide in the solar system. You can think of that as the asteroid belt, for example. All right, so now we come to the CHNOPS elements and linking their content in planets to the formation history in these disks. If you've seen a talk on a similar topic before, you will have seen this figure from Karin Oberg in 2011, but it really beautifully laid out for the community this concept. If you say that a planet forms in a protoplanetary disk that has a radial temperature profile where the temperature is highest towards the star, which is on the left in this case, and then the temperature decreases to the right as you go further from the star. And you also assume that the chemical composition of the disk is fixed everywhere. It's the same. It only contains water molecules, carbon monoxide, carbon dioxide, maybe some methane or some organic species. Then all you need to worry about is which species are in the gas phase and which are condensed into the solid phase, right? You're not worried about any chemical kinetics beyond these phase changes. So what she's shown here is how that leads to the ratio of carbon and oxygen in solids and gas changing as a function of location in a protoplanetary disk, right? And you can see the gas phase C2O ratio in her particular case for the composition that she chose to use, it increases with radius. So if you are a planet and you're accreting gas at 5 astronomical units, you will get gas with a lower carbon to oxygen ratio than if you're accreting at 30 astronomical units, right? So it's a beautiful little idea that says, well, if you then go and measure the composition of the atmosphere of this planet, even if it later migrates it to a different location around its star, you'll be able to measure the carbon to oxygen ratio, and then you can read off where this planet accreted its gas. So that's the idea. And carbon and oxygen are very nice, they're very abundant, they have a rich chemistry, many of the key species are relatively easy to observe, and both of these elements can be studied observationally in both planet-forming disks and in planetary atmospheres. So it's perfect, right? They're observationally accessible, and they provide sort of a range of constraints. Okay, this has been taken a step further. That's another example here from Karin Oberg. This is the Oberg and Wordsworth 2019 paper. So here they applied a similar, slightly more nuanced sort of underlying model to interpret the chemical composition of Jupiter's atmosphere. So on the x-axis are different chemical elements, and on the y-axis is their content in Jupiter's atmosphere, or so-called gas envelope, relative to the solar abundance, so which is the reference composition of the solar system, right? It's normally abundance ratios. If you just accreted material just like the sun, you'd get exactly an abundance ratio of 1 on this figure. You see that Jupiter is enriched in all of these elements. That includes the very volatile elements, carbon and nitrogen. There's still a lot of debate about the exact oxygen content of Jupiter. So you can pretty much ignore the black dot. And if you look at the blue line, I've maybe been a bit pessimistic, but I've given you some idea of what estimates have been published in the literature in recent years based on the most recent data on Jupiter's atmosphere. So there's a lot of debate, though there's a subset of the sort of work that really puts Jupiter's oxygen abundance exactly where the other elements are, at around 2 times the solar abundance. Okay, so the idea from this paper is that you can build Jupiter if you make a model just like the previous one that Karin Oberg had made. You say different compounds condense out at different distances from the star, and then you use more elements as your constraint. You can say, well, you can build Jupiter if you combine sort of some gas and some planetesimals, and then mix some fraction of the solids in the planet's core also into the gas envelope. That's the core dissolution, right? So you can sort of do some mixing between the core and the envelope, and you can add some fraction of gas, some fraction of planetesimals, and you can try to reproduce the abundance pattern of Jupiter. And the idea is that Jupiter is enriched in some elements because they were delivered in planetesimals that were destroyed, basically, or released those elements into Jupiter's envelope. Now, the key thing is in this work, the abundance of sulfur and phosphorus was assumed to be 100% in rocks, right? So even though there are 2 different elements used, they actually, in a way, provide exactly the same constraint in this particular study, because the assumption is that they just trace rocks, right? And that's the key point that I wanted to highlight actually about this work in terms of trying to understand Jupiter's accretion history. Okay, now to take a slightly different view, this is an example of a model from Diego Turini's group in Italy. There's also some really nice work from the same team by Elenia Pacetti. And what they've done is they also had essentially a planet formation model in a protoplanetary disk, coupled with n-body dynamics to simulate sort of the final outcomes for the planetary system. And they used more elements, right? Carbon, oxygen, nitrogen, sulfur, more than just carbon and oxygen. But in their case also, they have assumed sulfur to be entirely locked in rocks. And so even though you can see the other elements varying in abundance in the gas and solid phase, that's the solid and, the dashed and the solid lines, right? They just show, it looks messy, but basically you can see from the fact that it looks messy that carbon, oxygen, and nitrogen have a complex radial behavior in terms of their composition, where they are, right? Are they in gas or solids? For sulfur, that's not the case. It's just been assumed to be 100% in rocks that's not doing anything interesting in the disk. So it doesn't actually provide you with any additional information, in a sense, compared to any other measure of the refractory element content in a planet. So the question is this assumption valid, right? Is sulfur and phosphorus Does this give us a reliable prediction of where planets get their sulfur and phosphorus? Well, in their case, they showed some really nice plots, right, where you can see on the y-axis is elemental ratios. The different colors are ratios of different elements. And the x-axis is the initial location where a planet started to form. And in all of these cases, the final location of the planet was always 0.4 astronomical units. So it was a hot Jupiter by the end, right? It had migrated very close to its star, no matter where it started to form in the disk. And the idea here is if you take a combination of all of these chemical element ratios, you can read off at what distance from the star this planet started to form, even though the final location where you're observing this planet just by itself doesn't tell you that information, right? Because it's always the same in these models. Okay, so and sulfur plays an important role here because the reason that, say, the sulfur to nitrogen ratio behaves in this nice particular way is because sulfur is not doing anything. This is entirely contingent on the behavior of nitrogen. And again, those are things that we actually need to test with empirical data in disks in order to improve on models like this. This is, of course, in a sense, some of the pioneering work, some of the first to actually use sulfur at all to predict planet compositions. Right, now our laboratory is early type stars. I mainly want to just highlight here that early type stars, which are typically, we consider stars around 1.4 to 8 solar masses, let's say. You can also think, if you're an observer, like A-type stars, broadly speaking. The nice thing is we can observe a diversity of exoplanets around those systems, hot Jupiters, directly imaged far-out giant planets. We can observe really well-characterized protoplanetary disks and study their composition. And we can even study potentially the composition of planetesimals around these stars by looking at planetesimals accreting onto white dwarfs, which are the end state of A-type stars. So very interesting early type stars. And one of the interesting things, particularly about early type stars, is that we can study the chemical composition of the absolute inner regions of the protoplanetary disks around these stars by using accretion onto the central star. So for reference, it's really difficult to directly observe the chemical composition of the gas and especially the solids in the inner 1 or even 10 astronomical units, where most of the planets that we know are, right? So in that region where most planets actually are, it's difficult to get the disk composition directly, especially if you want to get sort of full details of many chemical elements. But what we can do for these early type stars is use the fact that they don't mix very fast. And if a protoplanetary disk is accreting very rapidly onto that star, actually the surface composition of the star is dominated by the disk, what the disk has just fed onto it. And that may differ from the bulk composition of the star. Okay, and so we've used this. We showed in past work that actually this works. The stellar surface composition depends on, for example, if dust is getting trapped in the disk. So if stars aren't accreting a lot of dust, we see a lower abundance of iron and titanium and so on their surface. We've constructed some models to help us to interpret these stellar compositions. We've applied this, actually, as I'll show in a moment, to learn something new about the chemical reservoirs of sulfur in protoplanetary disks. And then just recently, we now have a paper accepted on phosphorus for the first time in a protoplanetary disk to constrain the chemical reservoirs of phosphorus observationally in a disk. Right. We have complementary data from submillimeter observations. I don't have time to go through this workflow with you, but just to say that with submillimeter and radio telescopes, we can take spectra of, say, sulfur, carbon, oxygen, nitrogen, and phosphorus-bearing molecules in a disk. And if we have a good disk model, we can use that to infer the abundance or upper limit on the abundance of those elements in the gas phase. Okay, so we've used that as well for all of the different elements. The case study that I'll particularly show, a lot of this is based on work on the system called HD 100546. It's a roughly 2 solar mass star. Very prominent protoplanetary disk, really well studied, very well structurally characterized. It's known to have multiple dust rings where these so-called pebbles are getting trapped. As you can see in the bottom left panels, there's the left-hand panel shows you the innermost dust ring. Only LB data means basically it's very high resolution data. It's only sensitive to the smallest scale structures. So that's why you don't see anything else in that image. This is dust continuum imaging. And the dust ring size is around 20 to 30 astronomical units. On the right-hand panel in the same subplot, you can see the outer dust ring as well. And if you look at the spatial scales, it's around 1 to 2 arc seconds on the x-axis. And because the distance is 100 parsecs, that means the half width of these images is around 200 astronomical units. So there are two protoplanets known in this disk. One is inside the inner dust ring, and the other is between the two dust rings. So it's really exciting systems to characterize the chemical composition. Because it has these dust rings, we know that there's dust trapping that gives us constraints on the composition of the material. In terms of, if we look at the star, we can measure what has been locked into the dust ring. We can look at which elements are missing on the stellar surface, and then we can use that to learn, which elements have been locked into the dust, let's say. Okay, now on this disk, we had a really interesting case study from a former PhD student of mine, Luke Kite. He basically found, observing different carbon, oxygen, and sulfur-bearing molecules, SO and CS, that they are azimuthally very differently distributed in this particular disk. So now we're looking at chemical variations in the gas that are not only radial, as I showed you before with the ice lines, but they're also azimuthal. And so this was really interesting, and we decided to try to learn as much as we could from this. I won't go into the chemical line profiles right now, but feel free to ask me later about these asymmetric line profiles. The idea is that this particular strange azimuthally differing chemical composition, where on one side of the disk you're oxygen dominated with SO, that's an oxidized chemistry, and then you have CS, so sort of more reduced chemistry on the right-hand side, right, in this image. That can arise from azimuthally varying carbon to oxygen ratio in the gas phase. So on the bottom, Luke has reproduced those observations with a chemical model of the disk that contains exactly that, a sort of flip in whether the composition of the gas is dominated by carbon or oxygen. So that was a novel hypothesis that hadn't really come up before. This is a schematic showing this. So you have sort of normal disk conditions where the carbon to oxygen ratio is close to 0.5, which is what we normally would expect to see approximately. And then you have one azimuthal part of the disk where we think that potentially due to temperature difference, we're not quite sure yet, or illumination difference, let's say, the gas composition has changed. Some species have disappeared from the gas into the solids, and you end up with this high C2O ratio region. So again, I'll skip this in the interest of time, but if you're interested in the mechanism, you can ask me or look in Luke's paper. But the idea is that then if this chemical asymmetry is determined by something non-local, which we think is shadowing actually in the inner disk, then it may lead to a situation where in the disk atmosphere, there is a sort of periodically flipping carbon to oxygen ratio from the point of view of the planet, as the planet is orbiting the star with a different period than this chemical variation in the disk. Now, we don't understand the full implications of this for planets just yet, and Luke and other collaborators are actually working on that to clarify that. But there is a suggestion here that perhaps in order to interpret the chemical composition of planets, we not only need to worry about how the radial structure of disks changes in time and how the composition behaves in radius, but also in azimuth around the star. So more complexity that actually obfuscates the picture for carbon and oxygen. All right, so the second case study I want to show you is sulfur. Now, the interesting bit with sulfur is, as I said, usually it's assumed to just be in rocks, but actually there are plenty of observations of star-forming environments and disks that show varying fractions of sulfur in volatile molecules, H2S, CS, SO, and OCS. Also, ices, we know in protostellar environments can contain these species. At the same time, in solar system solids, we see things like iron sulfide containing most of the sulfur. And a relatively recent realization is that also ammonium salts, which is here shown on the right-hand side, can contain a substantial fraction of volatile and semi-volatile elements like carbon, oxygen, sulfur, phosphorus, nitrogen, potentially. Yeah. So there is a whole range of contenders for where sulfur can be partitioned, and probably, to figure out the details of exactly how much sulfur is carried by each of these species and how that may change in time or place in a disk. That's sort of the open question. And we were able to use this accretion contamination a few years back to show that sulfur on accreting early type stars with protoplanetary disks actually correlates very strongly with refractory elements, but not perfectly. There's quite some scatter on the one hand. Maybe that shows diversity of behavior. Maybe it's due to observational uncertainties, not quite clear yet. But the statistical analysis we did, the inferred fraction of sulfur locked in rocks, something like iron sulfide or potentially ammonium salts, which are also relatively refractory. So the refractory fraction of sulfur is around 89%. It's clearly, in our analysis, it was meaningfully different from 100% refractory fraction. Okay. Now, whether in some cases it is 100% locked in rocks, that's not entirely ruled out, but at the very least, it shows there's potentially diversity because it could also be less than 89%. So if that's the case, then that potentially would show that in some cases you could have a significant percentage, 10 or 20% of sulfur in volatiles. And this was only possible thanks to stellar spectroscopy of disk hosting stars. Okay. Now, in this figure, I've shown from the left to the right the behavior of sulfur in different environments. We have the interstellar medium, which is just preceding star and planet formation. There, sulfur is contained almost entirely in the gas, as we saw at the beginning of the talk, right? Sulfur has a very high abundance in atomic gas. That's shown in blue, volatile phosphorus. Now, it was previously unknown where it was in protoplanetary disks, and our empirical data showed that it has a very high, but probably less than 100% refractory fraction, and that's sort of consistent with the low abundances of sulfur species that in a few cases been seen in the gas. So usually it's very low fractions of sulfur that are seen, but it's up to 0.1 or 1% of all sulfur that's seen in the gas phase. Some of it could still be hidden in a relatively sort of semi-volatile ices like or salts like the ammonium sulfate salts. So this is, to me, this points to the potential for diversity in the inner regions of protoplanetary disks in terms of what the sulfur budget is. This also doesn't tell us strictly about the outermost regions of disks, but even in the inner disk, there may be diversity. So that's all I wanted to say about this. Now our analysis suggests that in the inner protoplanetary disk, in the inner sort of 1 astronomical unit terrestrial planet region, if you will, or super Earth region, around 89% of sulfur, give or take, is contained in either iron sulfides or perhaps to some degree in ammonium salts. Right. Now, the next question is, can we do the same for phosphorus? And phosphorus, which has never before been detected in any form in protoplanetary disks. there is so I'm just going to skip this to say there was previously really no data on this, and hats off to PhD student Sandipan Bhattakur, who actually dug up spectra from the Hubble archive to carry out the first analysis of phosphorus abundance in a protoplanetary disk hosting star. And this was HD 100546, which I introduced to you before. On the top right, you see the UV spectrum from HST STIS, the STIS instrument on Hubble. And on the bottom panel, you see the constraints on the phosphorus abundance from one particular run of his analysis. And you can see on the x-axis the phosphorus abundance in the red line shows that which Sandipan measured for HD 100546. And in the gray dashed lines, you see the solar and the sort of inferred proto-solar phosphorus abundance. So that's basically how much phosphorus was in the starting material for the solar system. And the way you should read this figure is HD 100546 is accreting very phosphorus poor material from its disk. And that's consistent with depletion of other rock forming elements like iron, titanium, etc. And it's similar to the behavior of sulfur. So if Sandipan's value, best fit value is correct, then phosphorus is depleted on the stellar surface by a factor of approximately 8, which leaves some space for potentially a small volatile component of phosphorus. We don't have enough data yet to fully quantify that. So that will have to be the subject of future studies. But this is the first empirical confirmation that phosphorus with a relatively high percentage, certainly something like 90%, is locked in rocks in this protoplanetary disk. Right, so I've tried to show that here on the x-axis and y-axis, you have the phosphorus abundance. The x-axis I'm using here to show the same as in the previous panel, the accreting abundance, so the innermost disk abundance of phosphorus, as well as the solar and early solar system phosphorus abundance. And with the number 1, I've shown that for HD 100546, that represents the composition of the innermost disk that's currently accreting onto the star. That's inside the dust sublimation zone already. Now, the inference is that most of the phosphorus has been trapped in that main dust ring at around 20 to 30 astronomical units, which is outside of the inner giant planet in that disk. Now, we also have submillimeter data from the APEX telescope of PO and PN molecules, which carry volatile phosphorus. And this figure, I'll only say that you see here upper limits. That's all you need to know. We didn't detect PO, we didn't detect PN, and the observations were designed in a way as to give us strong upper limits on the volatile phosphorus abundance. So that's what we got. My then PhD student, and now Queen Mary postdoc, Luke Kite, did the analysis with the DALI code for this disk, and we we're able to find that we can constrain the gas phase, or let's say volatile phosphorus abundance, both in and outside the main dust ring separately. So on the x-axis, we've now added constraints on the volatile phosphorus abundance inside the dust cavity, let's say, or the dust ring. And on the y-axis is outside, so the outer disk, which is on scales of beyond 30 astronomical units or so. And that's the domain of the outer giant planet. It's because we didn't detect anything, all we have is upper limits, but you see that those volatile phosphorus upper limits are well below what's being accreted onto the central star. So that's a strong suggestion that most of the phosphorus that's reaching the central star is contained in small dust particles that are not trapped in the dust ring at 20-ish astronomical units. So a strong argument in a way against large amounts of volatile phosphorus in the disk. But as I said, we really need to quantify the exact percentage, and that's future work. Right, so with that, I think I've exhausted the hour of the seminar, and I'll leave you with this summary. So we're in an era of chemical characterization of planets, and we're looking forward to the Ariel Space Telescope in that regard in particular, but also James Webb. And I will just highlight that I presented to you a couple of case studies, hopefully illustrating that we have a lot of ongoing work developing understanding in the behavior of the CHNOPS elements in planet-forming environments, that we now need to propagate this understanding into planet formation models. Because some of the key assumptions, such as, for example, that sulfur only traces rocks 100% of the time, that these are not necessarily completely backed up by empirical knowledge. And so the key question is, yeah, how do we convert this into useful knowledge for planet formation models? And that's what some of the students in my group are also working on, including Anna, Can, and Jason in particular. So thanks for your attention, and I'm happy to take questions.
Hi, Mihkel. Very nice talk. I'm thinking about, do you have any idea about, you mentioned Luke's work on the azimuthal averaging CTO ratio, and then give a explanation could be shadowing and lower some regions, azimuthal regions temperature, and then change the CTO ratio. Do you think about any idea, like linking any dynamical hydro dynamical process to explain this? Do you get any ideas?
You'd have to ask Luke directly.
Oh,
So, since it's really his work, um, to my knowledge, there's not yet been any coupling with hydro models. But as to whether that's planned, yeah, you'd have to check with Luke.
okay, cool. Thanks.
Certainly something like a hydro model with dust evolution in it, or let's say small and large grains in it, and so on, might be useful for helping to quantify if this can have an impact on the planet compositions. I would say that much, that certainly could be useful. Yeah.
Okay, cool.
Yes, Henri Wandel. You can ask your question if you want. Yeah.
Yeah, I was muted, so okay. I also enjoyed the talk, and I was at the end you talked about phosphorus, but at the very beginning you showed this figure about the abundance of interplanetary or in ISM phosphorus, and it seemed to be quite similar to um, more to the more volatile elements like
Yeah.
and
Uh,
I wonder why you put it in a different box. Why didn't you put it the same like Na and the other elements?
yeah, that's because it was easy to categorize elements here by condensation temperature, which in a way is one way to have an expectation on where that element is. In the ISM, yeah, it's true. Phosphorus, it does have, if you look here, right, this is a logarithmic y-axis. So actually the gas phase abundance of phosphorus naively here, you could say, is perhaps something like, a few tens of percent of the total phosphorus abundance, which is entirely might be allowed by our disk work now as well, and Sandipan's analysis of the stellar composition. Actually, it's really unclear whether phosphorus undergoes now any chemical transformation on its route from the interstellar gas, diffuse gas, into protoplanetary disks or not. For sulfur, the story in that sense is much more complicated because sulfur starts out here basically entirely as atomic gas and ends up almost entirely as rocks. Whereas for phosphorus, we see that even though it looks high, it's a logarithmic plot. So even there, it's actually, only 10 or 20% of the total phosphorus. Well, perhaps it's 20 or 30%, but yeah.
Yeah, I was just referring that it is very adjacent to Na.
Mm-hmm.
So
Yeah.
why they
Yeah.
put it in a different?
Yeah, it's just based on the condensation temperature, the 50% condensation temperature. So that, of course, does not contain the full information about what the chemical budget of each of these elements might be. It just, in a way, says that at those high temperatures, already 50% of the phosphorus should be gone from the gas, and the uh, the data is, in that sense, you could say, well, it's consistent with that. While for something like sulfur, the story is much more suspicious in that sense, right?
Yeah. Okay. So I could have put this difference, understood that sulfur and zinc are different box, but Na and phosphorus are very near each other. So
Yeah, it's true, and I think it probably shows the complexity of the full chemical budget that elements can condense into and be converted into through chemical kinetics, and also probably differences in the sputtering. So in the ISM, energetic particles can sputter individual atoms um, from solids, and there might be differences there also between, say, sodium and phosphorus. I can't actually fully speak to that right now, but yeah, it probably points to differences in these sorts of things, that they have similar gas phase abundance, but very different condensation temperature.
yeah, well, I know that sodium has been detected even in giant planets.
Yeah.
Yeah. Okay, thank you.
Yeah, in the paper where we looked at sulfur, we also actually had a few data points for sodium and zinc for the accreting disk hosting stars. And so we have some constraints actually on the refractory fraction of those as well. It's just the data were very, the error bars were very large, so I didn't focus on that too much to, yeah.
Yeah, and Harry, please go ahead.
Hi. Well, I actually wanted to ask, have you ever looked at the software which is called HDust? It is used for modeling BE stars disk and B bracket E stars disk, so like supergiant stars. But I suddenly remembered about that because it contains, well, mostly it only contains like hydrogen and dust. So there are no other elements in the gas. Maybe it's not that useful, but well, have you any kind of
No, I don't have
knowledge
any
of the existence of
experience
this
with
stuff?
HDust, but I'm happy to look it up.
Yeah, it's quite extensively used in massive stars community. So it's not a question, actually. It's just, yeah.
No, that's fine. Yeah.